Hello, everyone. I'm Professor Sever, and today we're going to investigate this concept of one-sided limits. And here we have our first theorem, which is a characterization of the two-sided limit. What it says is that the two-sided limit, or the full limit, which we know to be two-sided, exists and is the number L if and only if the limit from the left is equal to L and the limit from the right is equal to L. This theorem is useful in those situations where you might have a piecewise defined function where the pieces obviously are defined on one side of certain values, but also maybe in terms of problems where you don't really have techniques to exist. And you can see here, I'm kind of focusing in on the absolute value because it kind of lends itself to this type of analysis as well. So let's look at these four problems and see how they work. Look at the first problem, and we want to show we're being told the result, the limit doesn't exist. And by the way, we know that. This is our first canonical examples of where a limit doesn't exist. We know what the graph looks like. So it's a step function. We have a non-removable or jump discontinuity here at 0. But let's show that this limit doesn't exist, not using the epsilon delta technique as we did before, and not using the graphical consideration, which I did just by looking at it. Let's start by investigating both of the one-sided limits. Here's what we'll do. The limit, x goes to 0. And you can do this on any problem. Investigate the limit from the left and the limit from the right. Turns out in a lot of problems we don't need to do that until we get to this portion of the course where we're now looking at things that the analysis has to go a little more carefully. So now, here the limit is going to 0 from the right, so that means we're on the right hand of 0 on our graph going this way. And if we're on the right hand of 0, we're positive. And so now let's use our nature of the absolute value. What is the absolute value of x when x is positive? Well, that is just x. So now we know that from our theorem, functions that agree on all but one point, this limit is just 1. So we have established the limit from the right. Now, if this full limit exists, then the limit from the left would have to produce the same number. And if the limit from the left didn't produce the same number, or if it didn't exist, then that would be enough to say that the full limit didn't exist. That's what's going to happen here. Let's see. Now we're looking at the limit as x goes to 0 left of our same function. And again, we have to use the nature of our function, which here is the nature of the absolute value. And if you're on the left-hand side of 0, you're negative. What does the absolute value do to a negative number? Well, it leaves it alone. So the absolute value of x is minus x. And again, from our theorem, functions that agree at all but one point, we cancel, in essence, in the limit, and we get the value of -1. So we get the value of -1. Now, these values are not the same. So since the limit from the left is not equal to the limit from the right, they both exist and they're different numbers, we know the full limit doesn't exist. And that's because of our strong characterization in that theorem. It was an if and only if. So this one doesn't exist. And that's how such a problem would go if you evaluate or investigate the limit from the left and from the right separately and you don't get the same number. Let's turn to our second problem. All right, we're going to do the same thing. Evaluate the limit, or investigate rather, the limit. X goes to 0 left and from the right. It doesn't matter. I'm starting with positive for no particular reason. So we look at the limit from the right, we recopy our function in the limit. And again, we're on the right-hand side of 0. So what does the absolute value do to numbers that aren't 0? Well, returns the same value. So this is 1 minus 1. Establish the limit from the right. Now let's establish the limit from the left of the selfsame function. Okay, so again, we're on the left-hand side of 0, so x is negative. When we remove these two absolute values, in turn, we're going to get negative x result of the absolute value. Why? Because absolute value, negative number, negative of what the argument was. positive, namely, and that's how it becomes positive. And rewriting just so we can see it. Here we have negative times negative is positive, of negative is over plus. Okay, picking it back up. So since the limit from the left is equal to the limit from the right, and that says the full limit exists, therefore the full limit would be that common limiting value that says the full limit as x goes to 0 is 0. And we have concluded that problem. That's another good example. And by the way, just as an FYI, it's interesting, and you can do it as a little challenge. You can evaluate this limit without doing the limit from the left and from the right. Kind of neat to do it, but it's a good illustration of techniques for the one-sided limit. Okay, let's go to our third problem. Now, this one is not our first favorite limit with the sign limit of sine x over x as x goes to 0, which is 1, because we don't have the absolute value at the bottom. And again, it's certainly 0 over 0 form, so that means we have to do more work. And by the way, so were the last two problems. Well, this one wasn't. This was undefined minus undefined, and each limit separately was 0 over 0. So undefined minus undefined is certainly indeterminate, and it turns out we got 0 as a result. In our first problem, we got 0 over 0 form again, and that was indeterminate. And it turns out that did not exist. Okay, so back to the problem at hand. Once again, this has 0 over 0 form, which means we have to do more work. It's indeterminate. So let's see how that work pans out. And what we're saying for this example will be done through the analysis of the one-sided limits. Okay. So again, we're seeing this aspect of the absolute value several times. X is positive, going to 0 from the right. Therefore, the absolute value of x is positive, and it's equal to itself. Remove the absolute value terms. Now, this is our first favorite trigonometric limit. That's 1. Well, that's one side of it. Well, if the full limit goes to 1, then so does the one-sided limit. That's using this characterization theorem, again, for the establishment of the one-sided limit. Since the full limit is 1 of, here's how it would look. All right, we know that the full limit 1 here. Therefore, the one-sided limits have to be 1. The limit from the right, that also has to be 1. And that's what I used here. Okay, let's do the limit from the left. When I remove the absolute value. Now we're inside the sine function. Now this is an interesting property. We don't have to use this. We could use change of variables, but it's easiest to use the property. Sine is an odd function. Negative can come outside. And now the negative limit. And I could have done that all in one step. And here, once again, we have the one-sided version here, not including the negative of our one-sided limit. That is negative 1. Now, this number is not equal, not the same, this number. So just like just as it was in our first problem, since the limit from the right exists and is not equal to the limit from the left, then the original limit cannot exist. And from the graph, what do we know that's happening? Well, we kind of see there should be a jump in the graph. The right-hand side is going to 1. Another good example of one-sided limits used to evaluate a situation where it might have been a little tricky because of that absolute value. Let's look at our next problem. So here we have, again, a problem with absolute value in it, but it's a little different. And again, I can do this problem without investigating one-sided limits. I can do that by multiplying top and bottom by absolute value of x. But that's a little tricky. Say you didn't think of that, then you wouldn't know to do that. That's the advantage of one-sided limits. So again, what happens to the absolute value of x when I'm on the right-hand side of 0? Well, the absolute value of x is just x again. So bottom, denominator, I'm going to remove the absolute value of x. See the cancellation. Now this is just sine of x squared. And now that is just sine 0, which is 0. Okay, let's do the limit and see how simply that last version happened. because when we took out the absolute value, it became much easier. All right, so let's do it again. What is going on with the absolute value of x when x is left-hand side of 0, namely when x is negative, or the absolute value of x is equal to minus x. So the value of x is equal to this. Now again, we cancel here. Don't forget about the negative. So the negative 1 will come outside, sine of x squared, and that again, sine of 0, same value, say that they're equal. That says the limit. The original problem that we're working on, the limit exists and it's this common value. Write that conclusion. So since the limit from the left is equal to the limit from the right, and what value is it? 0, or work above. Then the full limit exists and is equal to that value. So the limit is x goes to 0, x times the sine of x squared over the absolute value of x, 0. And see, it's a nice theorem. It might worked out nicely, and you see there isn't really directly any cancellation that you can do between these two terms, because of course they're not algebraically equivalent, and separately this limit doesn't exist. So if we analyze this form at one level, if you looked at it as the numerator, it goes to 0. Over the denominator, it goes to 0. Then that would give you 0 over 0 form, which is indeterminate. If you analyze it a separate way, say this way, the absolute value of x over x, which we know is d and e, that's our first problem of this video, times this piece, which is 0, you would have 0 times undefined, which again is indeterminate. We don't know what that is. And in this case, the answer comes out to be 0. So again, nicely done with our one-sided limits. That was a quick overview and application of one-sided limits in terms of taking the full limit, breaking it down into its constituent or separate one-sided limits, and determining if each of those exist and equal the same number. That's one way to use one-sided limits as they assist the evaluation of the full limit. I'm Professor Sever, and I hope you enjoyed this video. We'll see you next time.